Alright, are we live? Hello? I think we're here. Welcome. Oh boy. Whew. I'm really tired. I went ahead and I did finally went to the gym. I had a hard time sleeping last night because I'm so actually frustrated, stressed out. I've got a lot on my mind, a lot of very difficult things, extremely difficult things. Yeah, well, hard to fully appreciate how difficult these things are. But yeah, I had a hard time going to sleep, and a hard time when I got up this morning. I went to exercise, and no, I didn't get sick, but I got a cough. So I keep my voice kind of low, but I'm tired and kind of not worn out, but not as comfortable as I could be, I guess. Anyway, it's good. It's good to exercise. It's good to exercise. But here we are. Take a look at the next problem. So I goes, I'll try to get as many problems as I can in today. Just kind of have at it. Integer n, return the least number of perfect squares that sum to n. Perfect square is an integer that is the square of an integer. In other words, it is the product of some integer with itself. For example, 1, 4, 9, and 16 are perfect squares, while 3 and 11 are not. Example, input n equals 12, output 3, 12 equals 4 plus 4 plus 3, 13 equals 2, 4 plus 9. Constraints 1 is less than or equal to 9, less than or equal to 10 to the 4th, so 10,000. That's interesting. Least number of perfect squares is sum to n. The smallest number of perfect squares. Okay. Well, this is kind of an interesting question. Let me think. 100, okay. So we have to look at 100 numbers. 100 squares to consider. I'm wondering, like, naive brute force algorithm, maybe there's a dynamic programming algorithm, and then maybe there's a more clever algorithm that's better than both of those. So brute force I guess would be a search, graph search. I think you'd want to do dynamic programming then, recursively, but basically the brute force is, if you know, given a particular n, you subtract each of those 100 perfect squares from it, right? All the numbers that are smaller that you can, and that each of those, that's one number, right? And then you take from each of those the minimum number of perfect squares that make up that number. Now obviously 1 squared is a perfect square, so you can add 1 a whole bunch of times. So every number will have a sum of perfect squares that will produce that number. So every number will actually have an answer. That's pretty much it. You take the minimum over all of those numbers. That's it. Now this is a little bit different from the previous question, because not the previous question, but there's an ugly number question that's similar. The reason this is different from the ugly number question is the ugly number question, it's not clear because we were given the index of a sequence number, it was a little harder, a little more challenging. Index in a sequence of numbers. We didn't actually know what the number was itself to operate on, if that makes sense. Like was a little bit special. So what I want to do is I want to program this in two ways. One, using recursion and memoization. That'll make it a dynamic programming solution, pretty straightforward one. The other one, excuse me. Actually, technically it's linear. It would be 100 times O of n, which is O of n. The other approach I want to take is actually the dynamic programming approach, or something similar, where you actually generate the numbers. Just thinking now if there's a way to do that, do both of them. Now the recursion with memoization, I think it's relatively straightforward to program here. The other way around, where you build the dynamic programming kind of solution, that, I don't know. Let me think. Let me just think here. Does that work the same way? We have an array of 100 numbers, and each one you're going to add some perfect square and take the minimum of all of those. And that's the next. It doesn't work like that. No, it's a little bit different. It's a little bit different. It doesn't quite work that way. That's interesting. Because it's not really a sequence of numbers. Not exactly. Excuse me. Yeah, this problem is slightly different. There's a difference here that's kind of hard to put my finger on, but we'll write the solution and go from there. So when I memoize, I tend to use I prefer to use an unordered set, an ordered map rather than an ordered map. Actually, just a map. I'll explain why. But it's actually just integer to integer. So yeah. So we can use unordered map. The reason why I would use a map typically is because there isn't really the most obvious support, hashing support for tuples and pairs for unordered maps. I actually could be wrong about that. It might be hashing support, but it gets a little bit a little dicey. But if it's only integer to integer, or in this case it is, then it's relatively straightforward. So we'll use recursion. Returns an integer. Have access to everything. Use f to recurse on itself. I have a base case. If n equals 0, use x. If x equals 0, you actually shouldn't really use this base case. It really should be, we'll just do 0. It gets a little confusing. We'll just say that's the base case. And we'll say for int 0 I times I is less than x So, or less than or equal to, could be. And start off with 1, really. Then you're going to say int ret with the minimum, and you're going to recurse on x minus I times I, and you're going to say memo of x equals ret, return ret. Okay, so now what this is going to look like is the maximum square is 100. Just one minor detail to throw in there. It's kind of important, kind of significant. And now we say, really, it's just I think it's that simple. I'm not really sure. Oh, I always forget that. Have to give the function to itself so that way it can operate. Oh, and one more thing. 1 plus 1 plus. All right, what are the other solutions? Let's go with all these numbers. Let's try like 10,000. That's probably correct then. 500, 750, 250, whatever, I don't know. I'm trying to think of something. Let's go for it. Yep, got there. Whoa! That is very slow. Oh. Okay, well, at least we got there. Why is this so slow? Want to go through all 10,000 of them? Whoa. No kidding. All right. So yeah, that's one approach. How long did that take? Less than 15 minutes. Nice. Now, excuse me. Could possibly do a little bit better than that. I don't know if this is much better, but I could try it. We want something like this. And obviously all the values are going to be non-negative. Do it that way. Does that still work? Is that better? That's a lot better. That's a lot better. Excuse me. Look at that. Talk about better. Talk about better. No kidding. Okay. That is a lot better. I guess the question is, let's go the other direction. Let's generate the dynamic programming solutions. So what we would do is we have the starting point, and we would generate all of the numbers by adding to the starting point each power, and that gives us different numbers. And then we would say which of these 100 numbers do you add next? Just thinking, this is a different kind of a problem. The dynamic programming approach is slightly different. How you do this and how you do the other problem. I don't really know how to articulate it exactly. But these are different. There's got to be a better way to do this. Also a way that doesn't require so much memory usage. Right? Using a lot more memory than is required. Gotta be a way to do this. I don't spend too much time on it, but I do think it's worthwhile to have like multiple ways to solve a problem, to kind of know multiple ways. Could look at the discussion, but I don't really want to do that. I want to see if I could think something up here. So from 0 we add these perfect squares, and we get 1s in all of these spots. And then 2s are going to be from all of those spots. And then you add numbers again, and that gives you 2, and then you do 3 and 4, etc., etc. I guess you also want to have a bitwise operator, like a vector booleans to just check to see did we get the right number for that spot yet. Now it's interesting that we don't need as much memory as I've been using. That's kind of weird. I wouldn't really expect that. That might just be because I'm doing it with recursively. Excuse me, which uses a lot of memory. Alright, this is like potentially 100 recursive calls at each iteration, which is probably a lot more memory than normal. Yeah, I guess you could use a vector of booleans to check whether or not you've already visited that particular number and have a smaller number there. And just stop trying to follow that number then. Yeah, basically you take the set of numbers that have 1, 1, and all those slots, you put a 1 there. And the next iteration is all those numbers that are 1, you multiply them again, or you add these different numbers again, and put those at 2. Each of the numbers at 2, add everything again to go to 3. And the tricky thing about it though is it's kind of like a breadth first search with 100, with a, what do they call that, a depth of 100, a branching factor of 100, which is kind of a lot. Just thinking, how do I... Obviously, this is a lot easier for me to think about and program if I use just simple recursion with memoization. However, I'm wondering wondering how this could be done with using it. So basically this recursive search is like a depth first search, and then the memoization just reduces the amount of, reduces the search space quite a bit. Breadth first search should work the same as well. However, or similarly, however, I'm not sure exactly how I want to approach that, how I want to do that. I don't know. Could try something like this, I guess. Like a breadth first search might do it. Be a little bit different, but let's think about how that might be done. So I have a queue. We're going to use a queue. We're going to use a vector as well. Queue. And we'll have standard queue of integers, queue. And we're actually going to use I guess like a working set. We're going to do a level breadth first search, level by level breadth first search. And is that what we want to do? Just thinking. Yeah. Yeah, okay, alright. Let's do it this way. Just not, like not super comfortable, I guess. So we'll just say next set, or next level. And, alright. The first level is, so the queue, this is going to be kind of interesting. Let's start off at 1 is 0 is, so start to count as 0, right? And the level initially will be a 0, I think. say stage, or yes, stage, or we could say index 0, pushback 0, right? Yeah, I'll explain what's going on here. And we'll say while level dot empty, or better yet, let's do it this way. Auto. And that level, say next level. It's probably while count is less than n, really should be less than n. What we're going to do, this is kind of funky, but bear with me. Definitely an unusual way to do this. So while count is less than n, we say for each value in level, we have this next level, we're going to say this actually goes above. That was why I needed an outer loop. Next level, if, so we do if, so let's say int new val is going to be x plus, you're actually going to do for each of these values, you're going to say for int I is 1, I times I is less than or equal to, you want to do x plus I times I is less than or equal to n, really. I'm going to say int new val equals x plus I times I. We'll say if and we'll use this now. And now we can use an array, actually. We could just directly use an array of integers. You could even just do n, it's probably better. So I don't have to use as much memory. Let's go to n if memo of new val is greater than -1, or it's equal to -1, then memo of new val is going to be equal to the index, or we'll call it level number. Let's do it that way. Okay, so it hasn't been set yet. And if it has already been set, you skip it altogether. Now, if it hasn't been set yet, that's when you add this new val to the next level. Right, that's important. If it has been set already, then you don't consider it again. You just leave it out completely, because somewhere else in the algorithm we're going to pick that up. It's basically like a dead branch. As for each value in this level, we're going to run through all of the possible perfect squares we can add, and add those to our next level and memoize each of those. And here we're just going to call this a V instead of memoized, because it's not really memoized anymore. Not quite the same thing anymore. And then after this is done, after we've updated this next val, we're going to set level equal to next level. We're going to use move semantics. I think it already does. But just to be clear, I'm going to move next level into level. And then at the end of this, we should be able to return v of n, more or less, something like this. I don't know what this is going to do. This probably won't even compile. Time limit exceeded, okay. Oh, and we're supposed to increment the count. I forgot about that. Wrong answer, output 0. And I made one more mistake, which I forgot. Level number. The level number increases as well. Forgot about that. 2, got the 12 with 2. Okay. I guess initially it's 1 then. Let's just add more things. See how this goes. Oh, okay. Looks like it's correct. All right, let's try other things, you know. All these different possibilities. See how we do on each of them. Let's try 10,000. 8 milliseconds on 10,000, huh? Let's go for it now. Okay, that's better. Alright, that's a lot faster. So, part of the difference there was, so that's way faster, and a little bit better on the memory, although still using quite a bit of memory. The reason for that is, I think that one of the reasons it's faster is that we're modifying how much iteration we do based off of what n is, something like that. Really, isn't that big of it. I mean, we could have made the same change with the other code as well. We don't have we don't have any more extra function calls, so we have slight improvement on the memory there too. Still using, do still have a bit of that memory though from next level to level, doing the sort of the level order. Now I wonder if this actually does. I think it does a. I think it'll do a. It'll use move semantics automatically. Yeah, I think that really doesn't matter. I don't think we actually need to use move semantics there. Just thinking if there's a faster way to do this in a way that uses even less memory. It's going to be kind of challenging to you could do something like this. You could do something like this. How about that? Does that give you the same answer? That's a lot faster. All right, now how about this? How about this? Use Booleans, and you say false, and you say v of 0 equals true. And now you say same kind of deal, except now you terminate early. And you say if a new val, which is well, that's pretty interesting. This loop and this loop work together to make sure that sort of a pigeonhole principle, I guess it's called. I didn't really think about that. That's pretty clever. So if it's already set, if it's not been set, that's when we set this to true. We don't push anything back. I don't know. Yeah, we do still push the new value. What about this? Increment the count. Does that still work? Where we, instead of using a vector of integers, use a vector of booleans. Really, it should be really -1, I guess. Should never reach that. How do we do here? If we go submit. Okay, still pretty quick, but less memory now, right? Reduce the memory a bit. That's better on the memory. Now a challenging thing for we can do a little bit better, I think. Instead of using a level and a next level, trying to do a little bit better on the memory. We can go back to using a queue. We don't really need this anymore, do we? Well, yeah, that'll get set automatically. So we don't have next level anymore. We have so we push it and take the front of the queue, pop the queue for each X. We don't need that anymore. There's no level anymore to consider. We say for each value, we take these new values. If it's equal to n, we return the level number. Otherwise, oh, it does get a little tricky because oh no, that's not going to be correct. It's not going to be correct. You could do, go back. You still have this queue. You're going to do it this way. Yeah, okay. Doesn't really save much, do you? Yeah, okay, never mind. You kind of do have to do it level by level. Yeah. It didn't change much, huh? Oh, really fast, though. Very fast. But not, not using less memory, though. So that's the thing. We're trying to reduce the amount of memory we're using. What I want to do to not use so much memory is to not have to store this level at each point. That's tricky. That's tricky. Could um, hmm. There's a few ways to do this possibly, but if you could push pairs onto the cube, and the pairs have the level number associated. Problem with that though is the problem with that though is that we have like twice as much in the queue now anyway. You know, it doesn't really matter if we're if we're doubling down on we have double queues. If we're gonna just push those numbers in anyway. Kind of curious if we go back to integers, if this is, I mean, that's definitely more memory though, you know, a vector of integers versus a vector of booleans. It's way more memory. Not really sure how we can improve on the memory for this. It's probably, I want to say this is probably as good as I can do. So this is fast, but it uses kind of a lot of memory. The next question would be, let me check something. The next question would be, how do we clean up all this freaking schmutz coming off of my head? The issue that I'm seeing is maybe there's a way I can literally find just what I'm looking for kind of directly. So if I took the largest, basically a greedy algorithm, I'd call it, the largest perfect square, and start with that, and see if I can, start with the largest perfect square, see if I can find the, start with the largest perfect square that fits, that's smaller, that's larger than our number, so remove that, subtract it, and then try to basically fit the pieces in for the what's left over, if that makes sense. The problem with that, excuse me, is there may be a way to put together the value, the number that doesn't require maybe a way to put together the number that doesn't require it's not the best approach to start with the largest integer that fits, the largest perfect square that fits. Excuse me. Yeah, that's what I'm trying to say. So, because if you have something like, let's see, we said 4 squared times 3, right? So 48. Okay. So there's a 6 squared. 6 squared that fits, right? 48 minus 36 gives you 12, right? So 4 squared 3 times gives you 3. 1 gives you 12. 2 gives you 3. And then to get to 3, you gotta subtract 1 3 times. So that's obviously not the right answer, right? So so that greedy approach that I just described won't work if you just look for the largest perfect square each time. You've got to do some degree of load balancing here, which is why the dynamic programming approach works very nicely. But the problem with that is I'm wondering, why do I have to use so much memory? Actually, well, Yeah. Yeah, let's try that. I think actually it'll be less memory if we do pairs. Let me try that. The way that they measure memory is sort of like, it's like an average as the algorithm is running. I actually think it'll be better if we use pairs. I'll explain shortly why. Actually, I don't know. It might be worse. I don't know. I couldn't tell you. Excuse me. All right. So we have make pair 0, 0. Excuse me. Yeah. And we don't use this next level anymore. We just say, well, Q is not empty. Take X equal Q, so X equals Q front, we'll do val equals X first, level number X second, and now we pop Q, we say less than or equal to val, let's go to new val equals val plus if new val equals n, return level number. Right? If we haven't seen this number yet, then we're going to say set that to true, we've seen it, and now we're going to push on to Q the new value as well as our level number plus 1. And now we increment the count. So now the level number is baked into the right into the queue, so we don't actually need to have a sort of level, levels of queues that are sort of swapping between them. Let's see if this works. Does this compile? Wrong. Oh, nice. It's off by 1, right? I think so. Why is that? It might be. It might be because of that. Yeah, there you go. How do we do? Okay. A little better on the memory. Yeah, it was a little bit better. I thought it might be. So, we're doing better on the memory, but not perfect, not perfect. Now here's a question. Do we even need to check this portion? I think we do. I think if we don't, we'll run into problems. Yeah. Let's try this. Try something else here. Try something else. Let's do it this way. I don't know about this. That doesn't seem like a good idea. What we're about to do. This is definitely not a good idea. Alright. What does this look like? Does that compile? Wrong. Okay. Yeah, that's interesting. I don't know. What is greater than or equal to no lower bound? So basically the idea is if we've... Let's see what's happening here. The idea is that we're trying to... We generate all these numbers. No, it's... I don't know, actually. No, I don't know. I think I need to use something like that set or that vector. I don't know how I can get away with this without using that much memory. I guess I should look at the discussion. The problem is, or what I'm trying to do is, I want to say, basically, if we've already seen this number, then don't push it onto the queue. How do I know if you've already seen this number, though? Well, I'm thinking at least we can go to the bottom of the stack, you know, of there's like a smallest number that we've seen already that starts off at 0, and you say, you know, if this new value is greater than that, then we're going to push this new value, this new level number, onto the queue and increment the count. But if this new value is equal to the lower bound plus 1, which it is in some cases, we're going to move up the lower bound, right? So we basically discovered the next lower bound. And the idea is that eventually we're going to bump into this n. The first time we bump into this n, we just stop. We don't really care about all the other values of the numbers. I could try that even. I don't know what that would look like. Who knows? Freaking why not? Let's see what happens. No, I don't get the right answer. And why not? Oh, that's why. Oh, I see the problem. We don't have the right value for the count, so actually we don't even need that anymore then, do we? That's why we're getting the wrong answers. What is this? This is... interesting. Let's go. Oh, so we do get the right answer now. Yeah, no kidding. It's a lot slower. A lot more memory. That's interesting. I guess that makes sense. It's a lot more memory. Yeah, that's interesting. I don't know. All right, I'm kind of stumped. I think I'll go back to my this solution here. These two pairs and the levels or whatever it was. I'll use the levels in the queue. Is it this one? Oh, look at that. Was this the one? Yeah, this is pretty good. I like this one. 2 queues. One is a level, one is not. Got a level number. Keep track of. Got a, you keep track of which values you've already seen. All right, let's get the discussion. Let's see what we got here. 4 different solutions: BFS, DP, static, DP, and mathematics. Wow, no kidding. Static DP, C++, 12, Python, Ruby. Oh, square root roundabout. Oh. Square root n solution with math explained. Wow, I missed that one. I missed that one. You're kidding. You're kidding me. Whoa. Whoa. Alright, let's do these two. Alright, this is a very interesting question. This question has a whole lot of interesting stuff you can do. Many large test cases that it's worthwhile to keep data between test cases rather than recomputing from scratch. Slower languages. DP tells the numbers of squares needed for the first integers. Ask about a new n, I extend the DP just as much as necessary. Okay, this is from a few years ago. Let's see. DP size less than or equal to n. M is DP size. Squares int max. For I equals 1, so each of these squares less than or equal to m. Not really sure I understand. Square is going to be min of squares dpm minus I times I plus 1. Push back the dp into the squares dp of n. I was thinking something like this, but I was kind of struggling to formulate it. Excuse me. Static vector. Jesus, that's interesting. I'm a little confused. Oh, I would say don't use a static DP. That's not really kosher. Let's not do static DP. No. We don't want static DP. I don't want that. Oops. Okay. Okay. Okay, with the two solutions of breadth first search and dynamic programming, also quote-unquote copied Stephen Bachman's static dynamic programming solution and David Tan's mathematical solution here with minor style changes and comments. Thanks for posting the right solutions. Interesting. Okay. Okay. Dynamic programming, 440 milliseconds. That's really a lot of time. What did I get? I got like a few milliseconds, like 4, 8, 12, 16, whatever it was. What was mine, man? I think my solution's pretty good. Yeah, basic Q, and then the other one was it's pretty fast. What was? It was 8 milliseconds, 12 milliseconds. What were these? Oh yeah, breadth first search with like a terminate early. It's 12 milliseconds with the 8 milliseconds. That seems to be the fast one. The Q. Just looking, these are the same, I think, right? Yeah. Yeah, super speedy. So that's the breadth first search. Dynamic programming. Okay, 0, 0 for each I less than or equal to n. For each I must be the sum of some number I minus j times j and a perfect square number j times j. Yeah, right, that makes sense. So for each perfect square that's smaller than I, do we know that the perfect square's got to be smaller than I? Yeah, I guess that makes sense. Yeah. I guess I is what we're looking for, right? So then you say count perfect squares of I is going to be the minimum of whatever it is, and this smaller possibility plus 1. Yeah, that makes sense. Okay, fair enough. And then you just take the back, the largest value, right? The one at the end, yeah. And my depth first search did something like this, so that was like really awkward. It's really slow. Why was this so difficult for me? Why did I have such a hard time with this? Oh, because if you loop from I equals 1 to n, then sort of by induction you have all of these values. I don't know why I struggle with that so much. I mean, I did my Memoized depth first search, which was pretty slow. I mean, I improved it slightly, but it's still pretty slow. Why didn't I just do it this way? Just do it this way. I don't know why. I don't know why somehow this slipped my mind. But this is so much cleaner, right? Like it's so much easier to understand. The depth first search solution is like kind of awkward. It's fast, but it was awkward. I could show you what that one looked like. I think it was this one. That was the depth first search solution. It's equivalent to the one. Actually, I don't know. It's pretty clean too. It's not bad at all. Actually, I think it's this one. No, that was my first level solution. There's some optimizations I threw in there. Let me try this one again. Let me just not throw out this one just yet. That's pretty simple too. I have these two, right? Yeah. Just want to see if I optimize this slightly, if it's better. Yeah, it's definitely slow. But you can do n instead of, right? And that's faster, not much faster here. It's faster than this than this one, though. Quite a bit faster. Trying to figure out why. Oh, I do know why. Because we don't do this minimum. Oh no, we do. I'm sorry, we do. Yeah. I think I did the same thing, the ret max. Int max, everything starts off at int max. Oh, I didn't think to do that either. Yeah, you can set this initially at int max, and then find the minimums. You don't actually need to recurse like this. Just the difference is, this is a little bit faster because when you go backwards, you don't no, actually that's not really true. I don't know. Actually, I don't know. I don't know why this is faster. I couldn't tell you. But you could rewrite this as, which I actually happen to like how they did it. It's going to be I minus j times j. Something like this. Uh-oh. Oh. See how we do. A bunch of other test cases. See how we do. Okay, works. Okay, that's pretty efficient. Yeah, not too much memory, relatively efficient. But that's super clean, you know? That is super clean. And I just, for some reason, I couldn't think that through. You know, like that was like on the tip of my tongues, but I just didn't. You need to use induction and use a for loop for all of the cases below. Use an outer for loop to create that induction base, so you can just, you know, loop over everything and take the minimums, and boom, really straightforward dynamic programming solution. Really easy to understand, really easy to code it up. It's efficient enough, you know, it's plenty efficient. Uses, you know, reasonable amount of memory. Yeah, the other one I did was, you know, because you can do something like this too, which is the other sort of dynamic. This is a Memoized depth first search, which is pretty much equivalent to a dynamic programming solution. But it's also slower. It's quite a bit slower. So that's interesting. It uses more memory and it's slower. It's the same idea. It's just this. Here I guess you're building front to back, and here you're going back to front. Basically, you're starting with, I want f of n, and so now go and recursively calculate, you know, whatever previous thing I need, Whereas here we're saying, because we're throwing this into a loop, we have already calculated that previous thing. You don't need to go get it. You could just retrieve it directly because you've already done it, which is different, right? Because this creates a stack and goes through a bunch of stuff before it, and then it returns. It sort of says, "Excuse me, I need this thing," and then that thing needs that thing, and it kind of like sends out a line and then pulls it back through a stack, right? Each series of steps pulls back, and we get the result we need to get our final result, right, recursively. But here we actually have everything we need already at each step already completed, so it's a little different. It's a little different. I kind of need more practice writing my dynamic programming solutions like this. Yeah, I find it kind of challenging doing it otherwise. But anyway, so that's pretty interesting. So these are two different solutions that are both dynamic programming, and this one is depth first search Memoized. This is just DP, straightforward DP. And let's go to, so that's, yeah, okay, interesting. All right, it's good I looked at that. Static dynamic programming, 12 milliseconds. The least number of perfect squares sum to I, since this is a static vector. If we've already calculated the result during previous function calls, we just return the result now. This is, we need to incrementally calculate the next result until we get the result for n. So basically you can modify your function to use a static vector, which should speed up your we gotta get rid of that. You can use a static function, which should speed things up even more. So we say basically if, and we're actually going to say you actually, sorry, I'm just thinking, yeah, same thing. You can use the size now, right? So we can build this as you go. So if v.size is greater than or equal to n, if the size needs to be greater than n, then return v of n. Should really be 1, 0 initially, so we can just leave that out. So we're going to say I from really to v.size, which minus 1 or 0, really, yeah, v.size. Yeah, if, I gotta be a little careful here. If the size is 1, then we want to go to, let's say n is 3. We need I to go from 1 to 3, less than or equal to 3. Yeah, that's fine. And we're actually gonna push back on v. A value, which probably we're going to start with int max. Yeah, do it that way. And now you can say j equals 1, j less than I, v of I equals the minimum of these things. And then return the back. Something like this. Does that work? Oh, really? That easy? Huh. Oh, well, that's a lot better. Oh, excuse me. Well, that's a lot faster. Okay. Yeah, that's fast. Okay, I see that now. Yeah, so that's making it static between function calls. I forgot you could do that. You can actually, yeah, static dynamic programming is definitely pretty interesting. Right. There's not much to say about that other than basically you're gonna build the vector between iterations, and you're just gonna calculate the portion of the vector that you need, given the previous portion you already have. And you just keep extending it until you have everything you need, and then it's like very, very efficient. That's pretty interesting. So that's the fastest I got so far with the best memory usage so far. Let's see what the other solutions are. Mathematical solution, 4 milliseconds. Is square return public based on Lagrange's 4-square theorem? There are only 4 possible results, number of squares. So what is that? Better measurement, wrap the actual solution in a 10,000 loop. Got accepted in 344. Every time a 3 submits out, the wrapper should take about, oh wow. Tried a few variations, and this is the fastest I managed to do. Okay. 4 squares always suffice. What? Lagrange's 4-square theorem. Lagrange's 4-square theorem. Now this is interesting. Also known as Bachet's conjecture. Bachet states that every natural number can be represented as the sum of 4 integer squares. Also, I'm not sure. I should keep checking chat. Every natural number can be represented as the sum of 4 integer squares. That is, the squares form an additive basis of order 4, where the 4 numbers are integers. For illustration, 331 and 310 can be represented as the sum of 4 squares as follows. Know that 310 can also be represented as the sum of these 4 squares, as well as these others. The theorem was proven by Lagrange in 1770 as a special case of the Fermat polygonal number theorem. What? How do you prove that? What? No way. What? That's... What? Are you kidding me? Is this some kind of joke? What? Are you kidding me? This is ridiculous. How do you figure that? What? No. No. Huh. Huh. No, man. How? I can't even fathom that. 4 perfect squares, you add them together, any number can be written as 4 perfect squares. Any natural number. That is crazy. That's wild, dude. What? And that's actually a special case of a more generic theorem. Polygonal numbers. Brother. What? Oh, that is just wild. Every positive integer is the sum of at most n n-gonal numbers. That is, every positive integer can be written as the sum of 3 or fewer triangular numbers, as the sum of 4 or fewer square numbers, 5 or fewer pentagonal numbers, and so on. That is, the n-gonal numbers form an additive basis of order n. Brother. My mind has been blown. You've got to be kidding me. You've got to be kidding me. What? What? No. This is crazy. This is wild. No. That's unbelievable. Unbelievable. Wow. Wow. Stated 1638 without proof, promising to write in a separate work that never appeared. Lagrange proved the square case in 1770. States that every positive number can be represented as the sum of 4 squares, for example. Gauss proved that triangular case in 1796, commemorating the occasion by writing in his diary the line, Eureka! Eureka! Published a proof in his book, Disquisitiones Arithmeticae. For this reason, Gauss's result is sometimes known as the Eureka form theorem. The full polygonal number theorem was not resolved until it was finally proven by Cauchy in 1813. The proof of Cauchy did a lot of stuff, boy, in maths. Happened to be a fan of Cauchy. He's done a lot of interesting things. Proof of Nathanson is based on the following lemma due to Cauchy. So he's got another proof in 1987, 40 some odd years ago. Let's see, wait, that would be, no, sorry, 30 years? Let's see, 21 minus 13, no, 33 years ago. Am I crazy? That's not 33. That's 34. 34 years ago, okay, before I was born. Odd's positive integers a and b such that b squared less than a and 3a less than b squared plus 2b plus 4. We can find non-negative integers s, t, u, and v such that a equals s squared plus t squared plus u squared plus v squared and b equals s plus t plus u plus v. Whoa. 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 Pollock's conjectures. Additive number theory. Additive number theory is pretty wild, man. First stated in 1850 by Pollock, lawyer and politician, contributor of papers on mathematics to the Royal Society. Partial extension of the Fermat polygonal number theorem to three-dimensional figure-8 numbers, also called polyhedral numbers. Pollock tetrahedral numbers conjecture every positive integer is the sum of at most 5 tetrahedral numbers. Numbers that are not the sum of at most 4 tetrahedral numbers are given by the sequence of 441 terms, with 3, 4, 3, 8, 6, 7 being about almost certainly the last such number. Almost certainly. Interesting. Huh. Pollock octahedral numbers conjecture every positive integer is the sum of at most 7 octahedral numbers. Every number is the sum of at most 7 octahedral numbers. Conjecture has been proven for all but finitely many positive integers. Polyhedral numbers conjecture, let m be the number of vertices of a platonic solid regular n-hedron, n is 4, 6, 8, 12, or 20. Every positive integer is the sum of at most m plus 1 n-hedral numbers. Every positive integer is the sum of at most 5 tetrahedral numbers, the sum of at most 9 cube numbers, or the sum of at most 7 octahedral numbers, or the sum of at most 21 dodecahedral numbers, or the sum of at most 13 icosahedral numbers. Brother, what am I reading? What's going on? Oh, no kidding. Okay. Oring's problem. Each natural number k has an associated positive integer s such that every natural number is the sum of at most s natural numbers raised to the power k. For example, every natural number is the sum of at most 4 squares, 9 cubes, or 19 fourth powers. Waring's problem was proposed in 1770. Whom is named as affirmative answer, known as the Hilbert-Waring theorem, was proved by Hilbert in 1909. Waring's problem has its own mathematics subject classification. Waring's problem invariance. Wow. Diophantus. I know you know the Pythagorean theorem, a squared plus b squared equals c squared, but what about a squared plus b squared plus c squared plus d squared equals x. That's kind of interesting that the sum, every natural number could be written as the sum of the length of hypotenuse of two triangles which have natural numbers for their lengths. That's interesting. Huh. Is that right? No, that's not right. No, I'm sorry, that's wrong. That's not what it says. That's not the, excuse me. Not only is it not what it says, but it's just wrong. Because it's x plus y, it's not x squared plus y squared, right? Or it's a, or I don't know, alpha plus beta, not alpha squared plus beta squared. Really interesting result anyway. Pretty amazing. G of k denote the minimum number s of kth powers of naturals needed to represent all positive integers. Every positive integer is the sum of one first power itself. Some simple computations show that 7 requires 4 squares, 23 requires 9 cubes, and 79 requires 19 fourth powers. These examples show that these values Warren conjectured that these lower bounds were in fact exact values. Hardy and Littlewood, the related G of k was studied. Oh man, this is complicated. This is really interesting. That was amazing. But when you're dealing with counting, you get some interesting stuff. Huh. Wow. Gondor's 3-square theorem. If and only if n is not of the form for non-negative integers a and b. First integers that cannot be expressed as the sum of 3 squares. Numbers that can be represented as this are. So actually, not only is the 4-square theorem true, but the 3-square theorem is true, and you need only consider one more additional perfect square for the 3-square theorem, the 4-square theorem. Yeah, for these numbers, you need only consider one additional perfect square. Oh wow, that's amazing. So, well, that makes things easier, doesn't it? If you can classical proof. So Legendre and Lagrange, both names are confused quite a bit. Excuse me, both famous mathematicians that I often confuse one with the other. They also both contributed to a very similar problem. It's pretty wild. Alright, well, classical proof. Oh boy. It's probably kind of complicated. Hurwitz integers. Whatever that is. Oh, brother. When I start seeing omegas, I start getting a little uncomfortable. The Hurwitz quaternion. Some quaternions. Oh boy. Last time I tried to study quaternions, I was interested in game development, in 3D mathematics for game development, but oh boy. Quaternions things get pretty complicated. I also got stuck too. I got like kind of hung up on all of that. four-square theorem, special case. General solution by Ramanujan. Generalizations. Yeah, generalizations of maths questions are really interesting to me. Very neat, very nifty. Wow. Algorithms. Oh, Robin. He's got some interesting algorithms. Yeah. With his name on it. Randomized polynomial time algorithms. Computing a single representation for a given integer n. Expected running time O of log square n. Oh! This is only square root of n. You can even faster. You can go even faster. You can go even faster. Yeah. No kidding. No kidding. Wow. Wow. Number of representations. Jacobi's four-square theorem. Oh boy. Shiwei-san. Each natural number can be written as the sum of the sixth power over fourth power and 3 squares. It can be refined. It's necessary to use the entire set of square integers to write each natural number as the sum of 4 squares. Wherzing prove that there exists a set of squares such that every positive integer smaller than or equal n can be written as a sum of at most 4 elements of S. Can be written as a sum of at most 4 elements of S. Where's some interesting stuff, man. 1963. Number theory, combinatorics, and Sun Jiwei. Group theory, professor at Nanjing. Huh. His twin brother proved a theorem about what are known as the Wall-Sun-Sun primes, guided the search for counterexamples to Fermat's last theorem. Erdős's combinatorial number theory, covering systems restricted sum sets and zero-sum problems. EGZ. Huh. Abelian groups. I don't know much about abelian groups. Q series. Q Pockhammer symbol, also known as Q shifted factorial, a Q analog of the Pockhammer symbol. I don't know what that is. Any natural number groups and this is so an even square and 2 triangular numbers. Wow. Huh. Many open conjectures on congruences. 100 conjectural series for powers of pi. Wow. 2013, published a paper. Many conjectures on primes state that for any positive integer m, there are consecutive primes not exceeding, such that m In the paper, refined Lagrange's four-square theorem in various ways, proposed many related conjectures, one of which is Sons 1 through 5. Editor-in-chief of Journal of Combinatorics and Number Theory. Sons' Curious Identity. Wow. Wow. Following identity involving binomial coefficients. It's established in 2002. Huh. Huh. This whole thing is equal to x minus m times x choose m. Generating functions, priority in arrays, WZ method. Jensen's formula, combinatorial proof involving dominoes and colorings. Huh. Wow. Interesting. Yeah, pretty. I like those kinds of proofs. They're pretty neat. Two different ways to count the same set, and because they're equal, then you get some interesting result. Sorry, I just like math, man. But all right, so knowing that every number can be written as 4 perfect squares, so we only need to go through 4 numbers. How does that help us? Does it really help us that much? I don't know that it does. Because basically just means our depth first search only needs to go down 4 times. Well, I guess we can get right O of square root of n time now, which is pretty fast. Although we're already really fast with this dynamic programming, static dynamic programming solution. But I guess we, what do we do? Oh, I see, we don't use any memory. That's what we do. It just becomes super fast and doesn't use any memory. That's what we do. So, well, let's do something kind of fun. Excuse me. Oh. Wait. That's a lot. Actually, what I'm thinking is oh, this is gonna be interesting. Are you ready for this? Basically, test 1, 2, and 3, and if you don't have 1, 2, and 3, it's just 4. All right, what's the question looking for? It's least number of perfect squares that sum to n. The number, yeah. So, yeah, what's interesting about this is if it's not 1, it's not 2, it's not 3, it must be 4, right? It's always 4. So the set of 1s we know out the gate. The set of 2s, we can just take all of the 1s and the set of 2s would be that's why it's square root of n. You subtract the square root values and check to see if those are also square roots. And no, you don't want to do that. You want to do I mean, you really just want to do 3 iterations of the perfect squares, of the squares, yeah, squares less than n or equal to n, less than or equal to n, and if any of them are n, return that. Yeah, something like this, I don't know. How about this one? How about this one? Yeah. All right, so you have 1 routine, 2, 3, turn 4. Okay. And you're gonna say, same deal. I don't know, it's gonna be for, that's gonna be auto x in vals. Right? And you take each of these, you're gonna say x minus this value if no, right, new value x plus I times I, right, if new value is equal to n, return 2, and you're gonna insert say next vals. Do it like that. So we'll do next vals, insert new val, and now we're going to say vals is going to be equal to new vals, right? So that's going to be, we're going to use move semantics just because we can. All right, return 2, and then finally we do the same routine again, right? So I don't think this is the best way to do it, by the way. Excuse me. This is quite possibly not good at all. new value. This time it's if it's 3, and then you don't have to actually insert anything anywhere. So this is an interesting routine. Interesting way to do things. New vowels, next vowels. I did mean next vowels. Good catch. Let's go for it. How do we do? Oh, it's kind of slow, actually. Uses quite a bit of memory. It's still pretty slow. I mean, it's faster than a lot of stuff, but not what I was expecting. Not at all what I was expecting. Yeah, this is not the best way to do it, because this takes quadratic time, or square root time. This, though, should be actually linear time, because it's square root times square root. And then this one actually is technically linear times square root cubed. So actually, these are not the best way to do it. These are not the best way to do these things. What does Lagrange's formula do? Lagrange 3 square. I noticed that too. It was mentioned in Pachmann's solution. Pachmann. If and only if it's not of this form. Okay. First numbers that cannot be expressed as the sum of 3 squares are so all the numbers that are the 3 squares are this is kind of interesting. Huh. Excuse me. So we can actually identify the 3 squares directly by basically looping over A and B, and A is a logarithmic term, B is, I don't know, but everything that can be, all of these numbers are all these numbers are 4. I'm confused now. If they're of this form, then they can't be written as 3. So they're 1, 2, or 4. So those are the only numbers you have to work on to make sure if they're 1 or 2. Obviously, the first number, the ones that are 1, are straightforward. The ones that are 2 are kind of tricky, right? Could do it another way too, is try to decide is this number a perfect square to begin with? All right, let's try that. Let's try that. Oh. These numbers are small enough where the double should be able to, the precision of the double should be able to handle it. All right. You know, otherwise we'll do loops for this one. Or just do brute force kind of thing here. I don't know. Actually, all right, let's do this. So this is kind of what I had before. Whoops. Just want to see, do we still get the right answers? Oh, wow. Whoa. Whoa. It's really fast. What happened? Why is it so much faster? Excuse me. Why is it so much faster? Why is that so much faster? Why would that? Wait a minute. What? What is going on? What? Why is this lightning fast now if I do it this way? Huh? This seems so strange to me. Well, I can go even faster than these two, I think. So, the ones that are square roots, boom, immediately. The ones that are sum of two perfect squares. Like if we're looking at 9,000, you know, look at sum of two perfect squares. This is, I mean, it's potentially it's a square root plus a square root, right? Times, yeah, square root of n times square root. This is potentially linear, and this is also potentially it's also potentially you know, super linear. For some reason it works out, but how do we modify these? We just make these faster. I want O of square root n. Oh, I know. I can make this faster. X could be n minus I times I, and we can do the same deal. Int, excuse me, int, and then say if x times x equals n, turn 2. Right, that's a little bit better. Oh, wrong answer. Oh, no kidding. Whoa, whoa. Uh-oh. 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 No, not equal to n. It's x times x plus... No. X times x equals n minus I times I. Ah, there you go. That's what you want. That's what you want. Right, does that work? Okay, a little better on memory. Slightly, a little slower though, this time around. And the last one, I'm going to do this same routine to make this here. Move that loop. X equals square root of n minus I minus I minus j minus j, x plus j times j, turn 3. I don't need that anymore. Okay, pretty quick. Still using some memory though. Interesting. Okay. Similar kind of thing. Let's see what we get here. Alright, there we go. 100%. Sweet. Super fast. Super fast. Pretty good with the memory. Not perfect, but pretty good improvement. Now, what I want to say is that you can go even faster than this, because you want asymptotic square root time. So this is basically you know, constant time, effectively constant. This might be maybe logarithmic even. Right, this part. This is obviously constant. This is square root times whatever this routine is. If we say this routine is constant, then this is square root time. But this part over here is not quite square root time, which is a little awkward. This is maybe linear time. Yeah. So, and we're using a little bit of memory here, which is interesting. But that's pretty good. That's a lot faster. It's definitely a lot faster. Now the question would be, is there a way to use Lagander's formula? Now, excuse me, Pachman was able to do something pretty quick, but really interesting. Always suffice, and 4 squares only needed for numbers of this form. I know the answer is 1, 2, or 3, and I try to build n as sum of 1 or 2 squares. For that, I use a kind of 2 pointers approach instead of going through squares a squared and checking whether n minus a squared is a square, which would involve computing lots of square roots. Imagine you start with a equals 0 squared and b equals the floor of the square root of n squared. As long as a is less than or equal to b, either make a the next larger square or make b the next smaller square, depending on whether the sum of the 2 squares is too small or too large. Return true of 2 if it's exactly right. I'm not really sure exactly what he did there, but in order to improve speed further, I use that squares are sums of consecutive odd numbers starting at 1. For example, 25 equals this, and a and b aren't squares, but the corresponding odd numbers. And instead of computing the sum of the 2 squares, I just add or subtract from n, trying to reach 0. This way my main part doesn't even have multiplications, just simple addition, subtraction, comparisons. Whoa! The wrapper for better time measurement. Fast. Who knows the theorem beforehand? I did. I think this is something the interviewer is looking for. Depends on the interviewer, probably not, but so what? In case it was you who downvoted it, I'd like to ask you to consider. This might not be what an interviewer is looking for, or what one could come up with in an interview. It is a correct solution. It's a better solution. It contains good stuff that one can come up with. Squares are sums of odd numbers and how to use it most efficiently. I'm sure I'm not the only one here who isn't just here for strictly for interviews, but for interesting stuff and for fun. It makes me sad if sharing good stuff is downvoted, discouraged. Not fit for interviews for most people. That is discouraging. Oh boy. Unless I'm getting something's going on. I don't know if they're trying to reach me. This is a super interesting question, though. Yeah, obviously, I take a lot of time to kind of really absorb questions. Just thinking. It's a question that was posed to the team. I think he can get in there. They'll figure it out. He's trying to get access to something. I can't really talk about it too much, but I'll just say he's trying to get access to something. And I'm pretty sure I know how to get the access that he needs. But he should be able to figure it out. They'll be able to sort it out, whatever the issue is. And eventually figure out how to get access. So, I don't know what's going on here. What did he do? Huh. Return 4, return 3, return 1, return 2. What in tarnation? What in tarnation? Okay. So, okay, so let's start with the 4, right? So you really have it could be 1, 2, 3, or 4, right? If it's not of this form, then it's 3. Now the question is, though, even though it could be written as the sum of 3, is that the minimum? In other words, could you not have a number that could be written as 2 perfect squares and also written as 3 perfect squares? Does such a number exist? And I guess you could probably verify that right now, just out of the gate. To see. Yeah, for those numbers, it could be, 1, 2, or 4, right? Like, we don't know. That's the thing I'm kind of hung up on, is how do you actually use these? Well, if it's not 1, it's not 2, and it's not 4, then it's 3. And I guess somehow he's saying that somehow you know that it's not 1 or 2 if you get to here. Now, why is that? Well, you know it's not 3 if you get to here, I guess. How does that work? N modulo 8, 4, 8b view, divide by 8. If we divide this thing by 8 and the remainder is 7, then this is of this form, and it's not going to be 3. So it could be 1 or 2 or 4. And I guess somehow we know it's not 1 or 2 also for here. Now why wouldn't you just put this down? I don't. Okay. Well, n modulo 4 is 0. Divide by 4. I'm so confused. I'm so confused. Why? What? Huh. Okay, so if it's a power of, basically it's some power of 4, you're gonna divide by 4 repeatedly, and then check if this remaining piece is you basically check if n is of this form. If n is of this form, then it can't be 3. Does that mean it has to be 4? I don't know. I mean, also, by the way, that means that you managed to divide all the 4s out by the time you get down here. So you're left with a kind of a weird thing going on. Yeah, I'm struggling. I should say I don't understand the solution. That's it. I don't get it. I don't get it. What? Use the fact that 4s are always sufficient, and the fact that 4s are only needed for numbers of this form. Oh, how did you get there? Oh, it's if and only if. No, wait. Yeah, so, what? Hold on. What? I'm super confused. Okay. From the four squares theorem follows easily from the fact that any positive integer that is 1 or 2 mod 4 is a sum of 3 squares. Because any positive integer not divisible by 4 can be reduced to this form by subtracting the 0 or 1 from it. However, proving the 3 square theorem is considerably more difficult than a direct proof of the 4 square theorem that does not use the 3 square theorem. Indeed, the 4 square theorem was proved earlier, 1770. Oh. I'm not sure I really understand what I just read, by the way. Still kind of hung up on how did you get this? What do you mean? Why are you just dividing n out? What is going on here? Why is this the only possibility? Why? I must know why. Interesting. If you divide out all the 4s, and you got something 7 modulo 8, basically you won't be able to get there with 3 perfect squares. You won't be able to get there with 2 perfect squares. 1, 2, or 3 perfect squares won't get you to 7 mod 8. That's what I'm reading here. That's what I'm seeing. And why is that? I think it's because, right, if you have 3 possibilities modulo 4 possibilities mod 4, right? If you square these are still only a couple of 3 possibilities mod 4. If you take these possibilities mod 8, and you square them, you have 1, 4, 9, 16, 25, 36, 49, which then gives you 0, 1, 4, 1. 16 mod 8 is 0. 25 mod 8 is 1. 36 mod 8 is 4. And 49 mod 8 is 1. Right. Right. Which then means is that right? 48 times 7? 48, no. 8 times 6 is, I don't know. 48, gotcha, okay. Which then means with one perfect square, you can only get a maximum of 4, which is not equal to 7. With 2 perfect squares, you can only get a maximum of 5, which is not mod 2 mod 7 mod 8. But with 3, you can go 1, 4. Oh no, excuse me. Actually, 3 won't make it. You need 4. Can get you to 7. You need 4 squares. 2 squares won't get you there. Because the best you can do is a 4. You do 4 and 4, it goes up to 1. It goes back to 1. Do 4 and 1, it goes back to 5. It goes to 5, and obviously 0 and anything else is not going to matter. So you won't get to 7. That's why. That's why. And also interesting is apparently you don't even care about these multiples of 4. You only care about this. You're trying to count how many. Well, actually, you can even do. Well, hold on. You really only have 3 options, right? 0, 1, or 4 mod 8. Oops. Once you've reduced n all the way down. No, sorry. So what are the possible values you could have for 1 or 2? Well, I guess it doesn't matter. I'll just say what's confusing to me is that divide by 4 a whole bunch, and now you're going to take square root of n, which it's a little weird. Because I guess you don't really care about the. I guess that actually isn't the square root of n. This is something slightly different because you've modified n. So that's kind of what I'm getting hung up on. This makes sense to me now, though. Now I get it. But this minus equals b times b, b plus equals b plus 1. Not sure I really understand what's going on there. While a is less than or equal to b, if n is less than 0, increment n by this. Else if n is greater than 0, decrement n by that. Otherwise return, if a is less than 0, return 1, otherwise 2. And finally, if you get through all of that, return 3. Dude, there's a lot going on here. There's a lot of pieces here. I'm at least here. I'm here. This part I'm totally lost on because I don't see. Not only are you not using n because it's the 4. The 4 is removed, but you're using. Well, the 4s are removed. You're also using square root of n, which is totally confusing to me. So you take this n here, and you subtract this times the. I don't know, man. This is confusing. kind of two pointers approach. Instead of going through squares a squared and checking whether n minus a squared is a square, which would involve computing lots of square roots, imagine you start with a equals 0 squared, excuse me, and b equals the floor of the square root of n squared. Okay. And as long as a is less than or equal to b, either make a the next larger square, or make b the next smaller square, depending on whether the sum of the two squares is too small or too large. Return true. 2. That's exactly right. But in order to improve speed further, I use that squares are sums of consecutive odd numbers starting at 1. True. For example, 1, 3, 5, 7, 9. And a and b aren't squares, but the corresponding are odd numbers. Sure, sums of odd numbers, okay. Instead of computing the sum of the two squares, excuse me, I just add to or subtract from n, trying to reach 0. This way my main part doesn't even have multiplications, just simple addition, subtraction, and comparisons. I'm totally confused, just totally lost. But I don't know, what is he doing? He's a and b are some numbers, some values. I guess they're supposed to represent perfect squares, and you add them together and you get some number. I'm so confused. I think I need to go lay down for a minute, just ponder what's going on here. Sorry. One moment. Okay, that should be fine. All right, yeah, I'm thinking. I just kind of want to like lay down and think for a moment. Like, what is he talking about here? So basically, he's saying he's trying to avoid executing all of these square root routines, checking, trying to check whether this requires 1, 2, 3, or 4. So the check for whether or not you can only get there with 4 makes a lot of sense. But the check for 1 or 2 doesn't make too much sense to me. Excuse me. It's trying to avoid. Oops. It's trying to avoid as many perfect square calculations as you can, or square root calculations as you can. So really, all you're trying to figure out is if n. Now, I guess the thing that's kind of funky is once you've removed all of the powers of 4, that's a little weird because I don't know. It's like you've kind of changed the value of n quite a bit, haven't you? If you, I want to say that his function, I don't know. I want to say he's got a typo in there or something. You know. That's actually really what I want to say. Is that I feel like he has some kind of a typo in there because. Excuse me. That's not the same value of n anymore. If you divide by, I think what do they have? A 4 raised to the a. If you divide by 4 raised to the a, or you divide by some exponent of 4. It's not the same number anymore. Now I'm assuming that, I guess a few assumptions that I have to make is that he didn't make a mistake, and you can divide out that 4 raised to an exponent, and all the logic may still make sense. Something like that. That could be true. Or it could be some kind of typo. Excuse me. And, you know, I don't know. Yeah, so, anyway, let's focus for a moment, though, not on that portion of n, but let's just consider n in general for a moment. Well, I mean, clearly, you know, if n is a perfect square, in our loop somewhere in there, we want to sort that out. But I guess really what we're looking for is whether or not it's the sum of 2 perfect squares, right? That's really what we're looking for. And if it's not, now you could. Excuse me. I want to say somewhere in there you could perform a check to see if, I guess if one of the values is 0 squared, then you'd return a 1. If it's not 0 squared, you return a 2. Something like that. I guess that's probably what he did. So it's sort of like this check for sum of 2 perfect squares, where one of them could be a 0. In which case you would return a 1 instead of a 2. And then once you exit that loop, you find that you can't do it as 2 perfect squares, then you just return 4, I think. You return 3 after that. Yeah, you can't do it with 1 or 2, so it's got to be 3. If you can't do it, if you don't get 7 mod 8, if you don't get 7 mod 8 after removing all of the powers of 4, though, what's interesting is you couldn't. Yeah, you need 4 perfect squares. So if you have 7, if it's 7 mod 8, then you can terminate early. But for all the other cases, you want to check and see if you can get there with
First we'll check 1 or 2. And if you can't get 1 or 2, then it's got to be 3. Pretty interesting. The algorithm itself, that sort of pointer, I mean, you could literally just use a sum of the perfect squares where you have I and you have j, and you have I times I and j times j. And I guess you would say if you're too small, then you would increase I. If you're too large, then you would decrease j, right? You're going to move I and j closer to each other towards the center. Until, if you hit the mark, then you're in good shape. But if, and you can start off, let's say A at 0 on the left side. That would still be square root time if you did it that way. Like, that's the simplest approach I could think of for square root time algorithm that would check for perfect square with 1, perfect square with 2, or perfect square with 3. Yeah, pretty interesting stuff. The one issue you run into with a perfect square if you do it the way I was describing, is that you'd be multiplying your I times I and your j times j to get some value. And I think what Mr. Pachman was suggesting is that I times I and that j times j, those could be represented as the sum of odd numbers from, I guess it would be 1 to some value, which I don't recall actually how you figure out. I think it's like if it's 5 squared, then it would be like 4. So the sum of odd numbers from 1 to 17, something like that. Or no, is it not 4? I think it's a difference of 2. Actually, I think it's two numbers. So yeah, the sum of odd numbers up to 9. I want to say up to so 5 squared minus 3 would be 3. It'd be up to. I'm sorry, not 9. I don't even know. Let's see. Hold on. Let's go to 25. So you can just do 4, right? 1 plus 3 gives you 4. So that's 2 squared. Oh no, it's actually whatever this if it's sort of a squared, it's actually the sum of the first a odd numbers. Yeah, it's pretty interesting. But that's like if you go to 25, it's 5. The first 5 odd numbers: 1, 3, 5, 7. 1, 3, 5, 7, 9. 1, 3, 5, 7, 9. 1, 3, 5, 7, 9. 9 plus 7, 16. 5, 21. Yeah, 1 plus 3 is. No, excuse me. 1, 3 is 4. 5, 9. 7 is 16. And then 9 is 25. Yeah. Pretty interesting. Pretty neat. So, yes. So you have these. You get these numbers. Get up to 25. And then. So now the question is, okay, we've got this sum that we're working with, and we want to shift a or I times I, and we want to shift we want to shift I times I or shift j times j. So if we are going to shift if we're going to shift one way or the other, you're actually just adding or subtracting an odd number, right? And that odd number is actually exactly the same index of whatever a or I or j was. So like if I is 1, the odd number, that's the first odd number, which is 1. If I is 2, that's the second odd number, which is 3, which is 2 times 1 plus, yeah, 2 times 1 plus 1 is the second number. So 2 times 0 is this first number. So there's, you just subtract by 1 to give you the right index, I guess. So if I is 1, then the odd number associated with that index is, subtract 1 gives you 0 times 2 plus 1. Or you do the other way around, just times 2 and subtract 1. That's actually easier. Same index, just multiply by 2 and subtract 1 to get the right odd number. So that means when we shift our sum, when we increase the sum or decrease the sum, that means we're going to add or subtract an odd number, because that's actually what increases the perfect square to the next perfect square. That's why he was suggesting. Very interesting. So you start with the difference between n and these two values. So you got these two numbers, and one of them is 0, probably, right? So 0 squared is 0, which is I'm just thinking, how do we do that? 2 times something minus 1 to give you 0. What does that make it? Makes it a half. Okay, so forgetting 0, I guess, for a moment. Well, no, that's fine. I mean, you'd add 1, right? I'm just thinking, would you add? Two times that index. If your index starts off at 0, yeah, so really just have a difference. We'll call it difference between b squared and a squared, or j squared and I squared, where I is just initially 0. And if the difference is positive, then you update the difference by subtracting 2 times j minus 1, right? That quantity, subtract that off and decrement j. And then if the difference is negative, then you increment by adding 2 times I plus 1, or 2 times I minus 1, which I guess when that's a little tricky. If I is 1, then you want to add 2 times 1 plus 1. Why is it plus. Am I getting that wrong? Am I crazy here? What am I doing here? What? Wait a second. Wait a second. Wait a second. Take the square root of n and get some index. Let's say n is 25. You get 5. And you take that difference. If you add these two numbers, you get this difference. Yeah, that's fine. It's sort of that initial difference, and it's always going to be smaller, right? Because you're really just trying to figure out if you need to add anything to get up to either it's a perfect square out the gate and you're done, or you gotta add something. You gotta add a and then decrease b and then add a little more a and decrease b a little more. You gotta kind of back and forth, get that difference to 0. And that's it. And that's it. Yeah. And then if you can't get that to work, or you can't get none of the pairs work, then you return 3 and you're done. Now actually return 1 almost immediately. Right? I mean, realistically, right? With these numbers are small enough where you would just return it immediately. So you don't need to set a to 0, because I'm trying to figure that out. Like, what do you do here? What you do is you check is that square root. If you multiply that by itself, is that going to give you the number you're looking for? If it is, return 1. Otherwise, set b to be that square root value, set a to be 1, and take the difference between, add those two together, take the difference to be n minus those two things. And then if your difference is, you do a while loop until these indices collide. If your difference is positive, then you want to increase a by adding 2 times a plus 1, going from 1 squared to 2 squared, and then recalculate your difference, right? Just subtract that value off the difference. Really, it's just subtract. Yeah, you increment a, and then you first subtract that value, and then you increment a. And then similarly, if the difference is too small, or rather, the difference the other way, where b is too big, or j, I guess we'll call it b. B squared is too big. You want to subtract. So if you had like 25, 5 squared, that's 5 times 2 plus 1 is 11. No, that's not true. See, actually, in that case, you actually want 2 times that index minus 1. So that's kind of funny. It's the fifth number. 1, 3, 5, 7, 9. The fifth number is 2 times 5 minus 1. But when you're adding, so actually, when you're adding when you're adding the next, for the A, the second number, yeah, we'll do, two times that minus 1. You want to increment the index first and then add it, whereas on the other side you're going to subtract and then decrement the index. I think that's why it's confusing, is because inclusive and exclusive, I guess, something like that. You're adding another thing. The thing that you're pointing to, you've already included. In both cases, the thing you're pointing to is already included in your sum, but in one case you're moving it and then adding the next one, whereas the other case you're removing this one and then adding and then moving to the next one. Yeah, I think that's why it's confusing. One of the reasons it's confusing anyway. But I think I get it. And then if the difference is 0, then you return 1 or return 2. If the difference is never 0, if you get all the way through, then you return 3. And that's it, man. That's it. That's all you gotta do. It's super simple. I think I get it. I think I understand. Excuse me. Also, it's interesting. It looks like it never even does any multiplication. So his is even faster than I'm thinking, because he doesn't actually consider the squares themselves. He actually does something unusual. He does like literally the odd numbers only. How long have I been looking at this for? 3 hours. Should probably end this and take a break. He doesn't even there's a difference I'm talking about that I'm trying to figure out what's this difference we're dealing with. He doesn't even mess around with these odd numbers. It's I think I'm thinking these indices and adding and subtracting odd numbers. You don't even need to do that. You can just consider the indices themselves, I want to say, something like that. Because everything's wrapped in odd numbers anyway. Like you could translate all of your odd numbers to just numbers of these indices. And when you change these indices, you would modify the difference, and that difference also is somewhat translated. Does that make sense? I don't know if that makes any sense. I don't know. I'm just gonna code up what I think I understand. Go from there. I don't think we need to go that crazy where we're even removing the multiplications. It's definitely a little challenging to me. All right, this is what we're gonna do. So int x equals n while x modulo 4 equals 0. X divided equals 4. Alright, that technically takes logarithmic time, by the way. Although I think logarithm is faster than square root. But so we have if f modulo 8 equals 7, we have no hope but to return 4. Otherwise, we can say int a equals 1. B equals standard square root of n. So while a is less than or equal to b, we're going to say if b times b equals n, return 1. Right, just done immediately. If we're going to have difference equals 1 plus b times b, n minus 1 plus b times b, and we say if
difference is greater than 0, then we need to reduce the difference by increasing a. So a plus equals 1, and then difference minus equals 2 times a plus 1. Yeah, so you get the odd number from a. So you had subtracted 1 before. Difference is still positive. Now you subtract 3, basically swap 1 squared with 2 squared. It's actually the other way around though, as you can see, because a really would be 0, wouldn't it? 0 corresponds to 1. So now you've already subtracted the 1, you already subtracted the 0th index. Now you increment. It really should be the other way around. A is 1, that corresponds to 1, because you do, it's 2 times a minus 1. That's what it is. That's the truth. That's the truth. Right? 2 times a minus 1. Yeah, that's why. Okay, that's because this is the second number. Right? Else if diff is less than 0, now we gotta. Now we have we're too big. Or we added a, we're too high. Or we added some squares, we're too high. Now we need to decrease b. Now b is already there though. Diff minus equals 2 times b minus 1. Right? 25, square root of 25 is 5. 5 times 2 minus 1 is the 5th already. So you subtract that and then you decrement. Yeah. Do one before the other. And then we say else. Right, diff is equal to 0. Turn 2. Right. 4, 1, 2, 3. That's it. When the a is equal to b, I don't know what happens here. Let's see how it goes. Roll. Nice. 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 Excuse me. Come on, man. Which one is that? The second one. From the bottom, 1,000. What happens to the 1,000? Ugh. Alright. 1,000 comes in. And I don't think it's not 4, right? Definitely not 4. No. So we get 250 divided by 8. 0.25 times 8. So that's what? Wait a minute. What? What's 250 mod 8? I don't know. Okay, it's 2. Alright, thought it might be, but anyway. It's not 4. Perfect square of 1,000. 31. Square from 1 to 31. Right? 31 squared. and 1. 962. 1000 minus 962. 38. Okay. So difference is more than 0. We increment by 1. We subtract. So now we say, really 3 it should be, right? A is 1. Go to 2. 3. Subtract 3. Now we go to the next thing, which is 2 goes to 3. It's 5. 3 goes to 4, which is 7. Which, oh, I see. That's why he was just adding, because you're just incrementing to the next odd number, so you actually don't even need to change the index. You can just add 2 each time. That's why he was doing sort of a plus equals 2 and then a subtraction of that. So that's 7. Now we know subtract 9. 11, and then now we would subtract what do we expect here, by the way? Two. Really? 100,000 minus 2. Or rather, what are the 2 squares that give you 100,000? Well, anyway, so we'll hold on to that. Minus 3, right? Now minus 11, we get 13. Okay, subtract 13. And now we're up to now we go the other way. Now we got a 3 for this one. So we missed this one, basically. This perfect square, this is 31 squared plus how many did we go? 1, just 2, 3, 4, 5, 6, 7. 7 squared. By the way, I would not be able to get here with the in an interview. Forget it. This would take me forever. This would take me ages to do this whole routine here. I would not be able to handle it. The 5-minute solution that I wrote, I would be able to get no problem, but this is like so beyond what I'd be able to do in a few minutes. Obviously, it's taking me hours now to mess around with all this. Yes, this is correct. It's 31 squared plus 7 squared. Now minus 10, we get minus 31. So let's do. It's 31 times 2 minus 1. 949, which is 30 squared plus 7 squared. Which is right. Okay. That doesn't sound good. Good. All right. Now we're positive again. Now we keep incrementing. Now the thing is, we get pretty close. How is it that we don't get the 2 here? What is, pair for 1,000? I don't know, it's 30 numbers, right? 30, let's do like 15 squared. What's 1,000 minus 15 squared? What could these be? Could write a small loop right now, but let's do that actually. Make these integers. Oh. And something like this. What do we get? Is that 1 and 9? Oh. 100, 900? Really? Oh yeah. Wait. Oh. That makes sense. I didn't think of that. I didn't think of that. So my algorithm misses. You get 30 squared plus 49 minus 1,000. So we're at positive. Okay. So now increase A. We said A was what? 13 is 15 now. 15 is 36. Which 49 plus 15 is what? Yeah, that's about right. Right? Minus 15, so we have 36 minus 15 minus 17 minus 18. All right. That's pretty close. So 9 squared. Oh, no, it's not 18. It's 19 minus 19. Excuse me, 36 minus 17, and then minus 19. All right. So now we're at 0, right? What does this return to? Second one from the bottom. What happens here? We had something interesting happen here. We got to 31, subtracted, so 30 squared, and then we get one up to 10. We got 30 squared, 10 squared, difference, A is less than or equal to B. And that should have been it. We should have returned 2 right here. What happened? What happened in this case? 1,000. 1,000. What is going on? 1 in 961, 4, 9, 16, 25, 36, 49. That puts you over 1,000. 949. Whoa. Oh. What? Wait, what? What? Get 900, and then now we gotta increase it. Whoa! Why? What happened here? Why do we keep decreasing this? What's going on there? Hello? Oh. Oh, come on, man. Really well. Oh, that's gonna be hard to. It's a hard bug to figure out if you. The logic is correct, but you just programmed it incorrectly. This is one of the hardest ones, and you don't realize you did it incorrectly. Those are some of the hardest ones, man. There we go. That's super fast. How's that for a runtime and a low amount of memory usage? There we go. That's fast. That is fast. Probably not as fast as Mr. Pachman's here, but pretty quick. Yeah, you don't even need to use. You can use different values entirely. You could set A and B to be. You could set these to be the odd numbers represented by this, which would be you could even do it this way instead of you can actually just make A the odd number and then subtract by A, right? And then same thing over here. B is I guess B is that odd number. What is B? B is 31 squared. B is 31. Subtract 31 times 2 minus 1. 61. Yeah, you can readjust B. Right? That's to give you the same answers. I think it does. Speeds it up a little bit more. Even less memory required. Because you're not doing as many operations, I guess. Pretty interesting. Pretty interesting. Yeah, I think this is okay. Now, if you do something like this, now you get real fancy. I can get the wrong answer. Because it doesn't work like that. Because, yeah, this one you can put, you could do this, but the order of operations, the other one has to be the other way around, yeah. pretty interesting. Pretty fast. I kind of prefer to just leave them in different. I like that. Yeah, very interesting. Very interesting solution. I prefer this way over whatever he had before with excuse me. I mean, you could modify this to return 1. I guess if A is... Oh, that's what he did. He started A at -1. Oh, that makes sense. Oh, interesting. Okay. Alright, let's try that then. Let's do it that way then. So A is 0 initially. Let's just try that. Let's give that a shot. Say if A is 0 initially, and then we'll say A is less than 0. Return 1, otherwise 2. Oh, I see. Now if you do it this way, see, the reason why you want to do it this way is you don't want to rely on floating point arithmetic. Yes, because this is going to take the floor, and floating point arithmetic can throw you off the larger the values are. You actually probably want you got to be careful with this approach. You don't know what kind of value you're going to get for B. You might even want to go further and do something like I don't know, actually. Technically, you can get the wrong answer due to floating point arithmetic here. Yeah, it's kind of funky, but it's true. It's kind of funky, but it's true. This is pretty good, though, as it is. I like this. It's pretty simple. Pretty quick. I like that. It went from 1,000 milliseconds to 0 milliseconds. I like that. I like that for computation. All right, I think we probably thought about this problem to death. Obviously, there's more maths underneath in terms of polygonal numbers. What was that? That was the... What are these things? The Eureka theorem and the Warings problem and what do they call these? Additive number theory. Yeah, we delved into additive number theory and came up with some pretty... It came across some pretty interesting results that people have come up with regard to additive number theory. So let me go. Thank you all for watching and sitting with me through all of that. That was quite the adventure. That was like hours long. Went through all of that. I think I understand. I think I get it. For each of these. Obviously, this part is kind of a this is pretty complicated. These two pieces, the 3 and the 4, those parts are kind of hard to understand. Those are from 3-square theorem and the 4-square theorem, which obviously we didn't go into the proof of those. But this part should be relatively easy to understand. This is kind of that's sort of a sliding pointer, or what do they call it? Yeah, sliding pointer kind of solution. I forget what the name of that is. What do you phrase it? How you call it? It's I like to think of it like sliding window, but that's not really. Just two pointers that come together. Like that. I've seen that. It's quite a few problems that use a similar sort of a solution. Anyway, alright, I'm gonna go. So, thank you again for watching, and I'll talk to you soon. Have a good rest of your day.